So we're going to continue with Chapter 8, the atmospheric environment. And this is one of 3 videos on the greenhouse effect and greenhouse gases. So this video is primarily just an introduction to the greenhouse effect, and it's going to show through a few simple calculations that in fact our atmosphere is absorbing this energy from the sun and creating a climate that is actually livable for organisms on Earth. And so let's start by just looking at the energy coming from the sun with respect to latitude. And so we do see that most of the energy is absorbed at the equator, but when we see in terms of outgoing radiation, so this is the radiation that is absorbed by the material on the surface of the Earth, but then radiates outward at different wavelengths. We see that it is distributed towards the poles. And this is because of the circulation within the atmosphere allows for this distribution of energy. And so before we get into the greenhouse effect and also the calculations, I want to review very quickly the electromagnetic spectrum. So recall that in the thermosphere, we have the absorption of the high energy wavelengths from the sun. The sun is producing gamma rays and X-rays, but in the thermosphere, the oxygen and nitrogen molecules are absorbing these wavelengths. Also, in terms of the far UV, the far ultraviolet, that is being absorbed by the ozone layer. So wavelengths below, say about 350 or so, don't quite make it to the Earth's surface. And so what we're interested in is kind of this window of the electromagnetic spectrum. This window includes the near ultraviolet, the visible, and the infrared. And so most of the figures will be dealing in nanometers. And so the visible is between 400 and 700, typically. And then what we have below 400, that's where we have our UV, and above 700 is where we have our infrared. That's the quick way to reference each of these categories of different types of electromagnetic wavelengths. And then there's also longer wavelengths that we will not discuss in this lecture. And so here again, we have a different view of the energy coming in and the energy coming out. And so what we see is that what's coming in from the sun, at least most of the energy, is kind of centered somewhere in the visible range. And we see that when we look at the sun, we see that yellow color, which is at about a wavelength of about 500 nanometers. And then the outgoing, though, is shifted way to the right, and it is in the infrared and shifted so far down that we call this thermal infrared heat. And so we see that the wavelength here, now this is in microns rather than nanometers, so right here we're looking at about 10,000, maybe 12,000 nanometers in terms of the peak of the outgoing. So before we do our calculation, let's look at what's actually measured in terms of what's coming in and hitting the Earth's surface. So this figure is saying that the peak intensity is at 483 nanometers, and the peak intensity with respect to what's going out is about 10,000. So I want you to remember both of these numbers as we do our calculations. So we're going to do two calculations, and we're going to show what we would expect the temperature of our troposphere, our atmosphere, to be given two different scenarios. So the first thing, let's define incoming solar radiation and outgoing radiation from the Earth in terms of symbols. We're going to use S naught for incoming and S for outgoing. And so the first calculation we're going to do is we're going to use the Wien displacement law to figure out temperature that we would expect given a model where the Earth is a black body. Now, black body is, there's a very exact or specific definition to a black body. It is something that emits radiation at all wavelengths, and it has a certain distribution based upon temperature. So you could just think of a glowing body, say like the sun. If we knew the temperature of the sun, we could use Wien displacement law and determine the maximum wavelength that that body would be given. It's emitting all different wavelengths, but this simple relationship allows us to find that maximum. And so we have a constant here that we can use as well. So what we're going to do in this first calculation is we're going to first actually look at the sun, and we're going to see whether that 483 nanometer maximum intensity that we saw in the last plot, if that is a reasonable number. But then we're going to use the 10,000 nanometer intensity that we saw in the last plot, which was the outgoing from the Earth, and we're going to try to use that with Wien displacement law to predict the temperature of the Earth. So let's do two quick calculations using the Wien displacement law. The first, I want to check to see what the maximum wavelength is coming from the sun. So we know that the temperature of the sun is 5,800 Kelvin. And so when we put it into the relationship using the constant, we get a maximum wavelength of 4.99 times 10 to the negative 7 meters. If I convert that into nanometers, there are a billion nanometers in every meter, I get 499 nanometers. That's very close to what was measured in the previous figure, saying that the maximum intensity was 483 nanometers. So most of the energy coming from the sun is in the visible region of the electromagnetic spectrum. And so now let's treat the Earth as a black body. It is radiating all wavelengths, let's say, but its maximum wavelength that it is radiating is 10,000 nanometers. And that is what I got from the previous figure. When I put that into Wien's law, note that I change it into meters, I get a temperature of 290 Kelvin. So given the radiation that's being emitted from the Earth's surface, it appears that the Earth has a temperature on the surface of 290 Kelvin. And so that translates into 17 degrees C or 66 degrees Fahrenheit. So that sounds like a reasonable estimation of the average temperature on Earth. So let's do one more calculation. The second calculation is going to estimate the temperature on Earth given the balance between what's coming in and what's going out. It's kind of more of an energy balance type calculation. So we know how much energy is coming from the sun and how much heat that should generate, giving us temperature. And let's see if that's what we observe. So we have the Stefan-Boltzmann law, which relates the outgoing radiation with temperature. And we have a constant here of 5.67 times 10 to the negative 8 watts. So watts is going to be our power coming from the sun, entering the atmosphere, then leaving over a certain surface area, and then the constant to the fourth power. And so first, we need to kind of create a model for our calculation. So first off, we're going to treat the Earth as a disk. We know it's a sphere, but what the sun actually hits is more of a disk. Then we also realize that that's the way in which the energy is absorbed, but in terms of the way the energy radiates, it radiates from the entire surface of the Earth. So in terms of radiation coming from the Earth, we need to consider the surface area of the Earth, and that is this equation here. So we have these two relationships that we're going to take another step further. So in terms of the energy that we know is coming from the sun, we realize that not all of it is absorbed. Some of it is reflected back in terms of the tops of clouds, perhaps hitting ice, which is very reflective, and even water. So there's many different surfaces on the Earth that don't absorb the energy very well and reflect it back into outer space. And so what we can say is that close to about 30% of all the energy is just reflected back and not absorbed. And so if that's the case, then we can say, given what we described in the previous slide, that the outgoing radiation needs to consider the surface area of the entire Earth times kT to the fourth, which is S. And so this is our relationship describing outgoing radiation, taking into account the entire surface area of the Earth. Now, incoming, we need to treat it like a disk, and this is incoming, but we're going to subtract some of that which is being reflected. So A is for albedo, so we need to take that into account. We're going to end up entering 0.3 for this value. And so this simplifies to this relationship here. So this is the incoming. Now we know that what comes in must go out. And so we have this relationship as well. And so we put the two terms equal to each other and we simplify. And now we have a new relationship between what is outgoing and what is incoming. And again, getting back to the Stefan Boltzmann's law, S is equal to K temperature to the fourth. So this figure shows some of the surfaces that have a very high albedo, such as deserts and snow, ice, clouds, etc. And so we do get a value of about 30% in terms of energy that's reflected back. And so this figure, what this is showing us is all the different processes in which you need to take into account for full estimation of the radiation balance in the atmosphere. Our calculation is a simplification, but nonetheless, let's see what we get. So for our radiation balance, let's solve our new equation here. We have our constant, Stefan Boltzmann's constant, and we know how much energy is coming from the sun. And so this is in watts or power per surface area. And remember, it's hitting that disk. And so the Earth takes on this incoming radiation, and what temperature would we expect the Earth to be? So based upon Stefan Boltzmann's law, what we see is that the temperature should be 256 Kelvin, which is negative 17 degrees C or 1 degrees Fahrenheit. So well below the freezing of water. And so let's end this video with a quick take-home message. So using both the Wien displacement law and the Stefan Boltzmann law, we were able to determine that the Earth's temperature based upon outgoing radiation should be 290 Kelvin, and that is what we observe. However, if we were to consider the energy coming in from the sun and also consider albedo, reflecting some of that energy back into outer space, we would expect a temperature on Earth of 256 Kelvin. And this is a very reasonable calculation in terms of what we would expect the temperature of the Earth to be based upon the energy coming from the sun. However, this temperature of 256 Kelvin is what we observe at 5 kilometers in altitude. If you remember from the previous video, this altitude is where we have about 50% by mass of the gases in the atmosphere, 50% below 5 kilometers and 50% above 5 kilometers, going up to, say, 100 kilometers. So in reality, this altitude, we could say, is the middle of the atmosphere with respect to the amount of gas. And so it appears as though the Earth air system is radiating somewhere within the middle of the atmosphere. And so the discrepancy between the two numbers is about 34 Kelvin. That's a considerable amount of temperature. And what we can say then is that this extra temperature is due to the trapping of heat by greenhouse gases. And so the fact that we have greenhouse gases in our atmosphere allow us to have a planet with a temperature on average that is above the freezing point of water, which allows life to be a possibility. And so we'll continue talking about greenhouse gases in the next two videos.